Hello and welcome to the Unit 4 Section 3 video on key features of higher order polynomials. So what we want to do is we want to review a few things that we already know, because we're going to use a lot of things that we've already learned to move us into working with higher order polynomials. So the first thing we're going to do is remind you of a few things. So remember that polynomials have no variables in denominators or exponents. They have no roots, or at least they are not a square root, okay? So you cannot have a square root in a polynomial. They have no absolute value of variables, and all variables have whole number exponents. So you can't have x to the 1/3 or x to the 3/5 or anything like that. Okay, also recall what a function is. A function is something that has an input, which is our x, and then an output, which is typically our y. And if you're looking at a graph, it will pass the vertical line test, which means we can take a vertical line that's going up and down, and we could put it anywhere on the graph, and that function only goes through that vertical line one time, no matter where you are along the graph. So we've already looked at several polynomial functions, including linear, quadratic, and cubic. In this unit, we're going to continue focusing on higher order polynomials. Now recall that in behavior describes how the graph behaves at the ends in relation to the x-axis, okay? So we have, as x approaches infinity and as it approaches negative infinity, what happens with y, okay? So for the graph of a polynomial function, the end behavior is determined by two things. It's determined by the function's degree, and it's also determined by the sign of its leading coefficient. Okay, so if we know what the degree of the function is, whether it's even or odd, and we know what the sign of the leading coefficient is, whether it's positive or negative, then we can determine what the ends of the graph does for any polynomial. So let's start this from a basic view, okay? We're going to take a look at a quadratic and cubic function and figure out what that end behavior looks like. So let's start with a quadratic function, okay? If we have something that is even, okay, like x squared, the degree is even, so that 2 in our squared tells us that's an even exponent. And the leading coefficient is positive, which we don't have a negative in front of the x, so therefore it is positive. We're going to have a function that looks roughly like this. Now I'm not going to graph it exactly, we just are more concerned about what the shape is, okay? So when we graph it like this, our end behavior is as x approaches infinity, f of x approaches infinity as well. Okay, that's on the right-hand side. Let's look at the left-hand side. As x approaches negative infinity, f of x approaches infinity on this side. Okay, so what we're seeing here is in the even function, both as we go to the left and the right, y goes in the same direction. Okay, and in this case it's positive infinity. Well, what if we put a negative out in front for the leading coefficient? Then you're going to have a graph that looks roughly like this, okay? The parabola will be concave down. So the end behavior here, as x approaches infinity, f of x will end up approaching negative infinity. And as x approaches negative infinity, the same thing is going to happen. F of x will also approach negative infinity. So we can really take away from an even function, our f of x is either both going to go to infinity or both going to go to negative infinity, and we can say that for any even function. So this works for x to the 4th, x to the 6th, x to the 8th, and so on. Well, what happens when you have an odd function? Well, let's use a cubic function as an example. If the leading coefficient is positive, our cubic function is going to be increasing. We learned that at the beginning of this unit. So it's going to look something like this. So as x approaches infinity, we have f of x approaching infinity as well, because we're looking at the right-hand side. as x approaches negative infinity, f of x is going to approach negative infinity because we're looking at the left-hand side, okay? So f of x is going to approach opposing infinities because one's going up, one's going down. If our coefficient, leading coefficient is negative, like we have here, negative x to the third, then we're going to have a decreasing function, and it's going to look something like this, okay? So in this case, as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x is going to approach infinity. So again, our f of x goes into opposing directions, but this time the negative infinity for the f of x goes with our positive infinity for our x, because now we're decreasing. So we can port this to any odd degreed polynomial. So think about a linear function. If we have an increasing linear function, then we have the same end behavior here, because we basically have a straight line that's increasing. Same thing on this side. If we have a straight line that's decreasing, same end behavior that you're going to have here. And a straight line is a linear function, and that is got an odd degree. So you can see that it works for that as well. So let's do a few examples here. Let's describe the end behavior of each of these equations, okay? So we don't have a graph, but we do have the information that we need. All right, so for example A, our degree here is 7, because that's our highest exponent. So therefore, our degree is odd. And then our leading coefficient is positive. So we can take that information and we can sketch a little graph, okay? So it's going to behave very much like a cubic function because our leading coefficient is positive, a cubic function that is increasing. So the graph's going to look something like this. And so we can use this little sketch to write our end behavior. As x approaches infinity, f of x goes to infinity as well. As x approaches negative infinity, f of x goes to negative infinity as well. All right, for B, we have a exponent, or a degree, our largest exponent, of 10, which is even. So we have an even degree, and our leading coefficient is again positive. So this time we're going to have, since we have an even degree, we're going to have something that's kind of like our quadratic, where we've got a parabola that is concave up because our leading coefficient is positive. So as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches infinity on the other side as well. Okay, so let's go on to C. As we have f of x equals negative 6x to the fifth plus 14x squared plus 20. These other terms we're not really concerned about. It's mainly the first term that's going to give us the information we need. Our degree is odd because our exponent is x to the fifth, and our leading coefficient is negative this time. So we've got a cubic type function, but this time it's decreasing. So we're going to have something that looks like this. So our end behavior is, as x approaches infinity, f of x approaches negative infinity on that right-hand side. On the left-hand side, as x approaches negative infinity, f of x approaches infinity. And then finally for D, our degree here is 4, so it's even, and our leading coefficient is negative, so we've got something that looks kind of like a quadratic that's concave down. So as x approaches infinity on the right-hand side, f of x approaches negative infinity because we're pointed down. F of x approaches negative infinity. And then as x approaches negative infinity on the left-hand side, f of x also goes to negative infinity because it's going down on that side as well. All right, so we can figure out what the end behavior is looking at an equation. Let's see what we can do with a graph. So we're going to describe the degree and the leading coefficient for these graphs. All right, so let's start with A. Well, we've got something that is odd because one arrow is going up, the other arrow is going down. So that tells us that we have an odd degree. The leading coefficient, because we're going down overall, we're decreasing overall from left to right, our leading coefficient is going to be negative. Our degree for B is going to be even because both arrows are pointing the same way. Our leading coefficient is going to be positive because we're generally in a concave up sort of shape here. All right, let's move on to C and D. So our degree for this one is going to be odd because our arrows are pointing in different directions. And overall, we are increasing. So our leading coefficient is positive. And then for this last one, both of our arrows are pointing in the same way, so our degree is even. And because we're generally concave down, our leading coefficient is negative. All right, let's talk about turning points now. So the point in which a function changes from decreasing to increasing is also called a turning point. And I've kind of talked about this already in the previous sections, because back when we talked about cubics, we also talked about them being inflection points. It's where we change from concave up to concave down. At least in that case, it's an inflection point. But anywhere where we change from positive to negative is a turning point, okay? So let's take a look. Oh, and by the way, the graph of every polynomial function of degree n has at most n minus 1 turning points. So if your degree is 8, the highest exponent is 8, the most turning points you can have is 7. You can have fewer than that, but you're at most going to have 7 turning points. So let's take a look at a couple of examples, okay? So for A here, and you're going to have your notes in front of you, so you're going to need to utilize that a little bit to look at this graph, because we're going to go down and kind of fill in some of this information. So first of all, let's talk about the number of turning points. So we have 2 turning points here. One here, where we go from decreasing to increasing at 2, and then we have another turning point at x equals 4. Okay, so the number of turning points is 2. The relative minimum is going to be at 2, 0. The relative maximum is going to be at 4, 4. Okay, that's our point right there, 4, 4. That's our relative maximum. Again, refer to your graph for this. But since we know what our relative minimum and maximum are, we can figure out what our decreasing intervals are even without the graph. So our decreasing intervals are going to be from negative infinity to positive 2, union with 4 to infinity. Now remember, x equals 2 and x equals 4 are both turning points. And then where we're not decreasing, we're increasing. And that's from 2 to 4. All right, let's look at B now. The number of turning points we have here in B, well, again, we have 1 here and 1 here. So we've got 2 turning points again. Our relative minimum is going to be at 2, negative 1. Our relative maximum is going to be at 0, 3. All right, so our decreasing interval is from 0 to 2, and our increasing interval is where we're not decreasing. So negative infinity to 0, union with 2 to infinity. All right, let's move on to the next page where we've got a few more examples for you. So in these, we're going to determine what the zeros are. Well, the zeros are simply where the graph either touches or crosses the x-axis. So our zeros for this graph are -2, 0, and 1. Our positive intervals break up where we have the zeros, okay? So our positive intervals go from -2 to 0, union with 1 to infinity. That's where we're above the x-axis. That's where y is positive. Our negative intervals are basically where we are not positive. So -infinity to -2, union with 0 to 1. All right, let's determine our zeros for this next graph. We got -2, 2, and 4. -2, 2, and 4. Our positive intervals are from -infinity to -2, union with 2 to 4. Remember, we always use x values for intervals, except for when we're talking about range. All right, negative intervals are going to be where we're not positive, so -2 to 2, union with 4 to infinity. Okay, let's go on down to the next two examples. All right, let's start off with E. We have two zeros in this one, -2 and 1. So that's x equals -2 and 1. All right, we are positive everywhere except at -2 and 1, because remember, our value at -2, x equals -2, our y value is 0. Same thing for our x value at 1, our y value is 0. 0 is not a positive number, so that therefore those particular points cannot be included. So our positive interval is going to be from -infinity to -2, union with -2 to 1, union with 1 to infinity. And then our negative interval for this graph, well, there are none. All right, let's look at this last graph. So we have a 0 at -3, and that's our only 0. So we can just write x equals -3. We have no positive intervals. Everything's happening at or below the x-axis. Now for our negative intervals, we are going to have everything but -3, because -3, the value is 0, and that's not negative. So we've got -infinity to 3, union with 3 to infinity. Okay, so for this last section, I'm just going to briefly go over how to do this. I'm not going to show you with the graphing calculator how to do this part. If you need a little bit more detail on how to use your graphing calculator to do these things more specifically, I would refer you over to the section 3.1 video where I went over how to find zeros using a graphing calculator. If you can do that, we're going to be doing that again here, but we're also going to be doing the minimum and maximum. And those are also found in the same calculate menu in your graphing calculator in your TI-84 Plus. And you're going to do the same thing to find your minimum and maximum. You're going to set your left bound, your right bound, and then take a guess somewhere in between. And your calculator will give you both x and y values. So I'm not going to go over that. If you need to see that again more in detail, head over to the section 3.1 video for that. What I'm going to do is show you how we are going to use that information to determine a few things, okay? So I'm going to go through this first column in this example, and I'm going to go ahead and show you what to do here. And then after I do that first example, I will provide the information for the other two. That way you can use that information to practice and see if you can get the same thing that I got. All right, so for the first example, the number of turning points, you can actually see that in this kind of picture of what you would have on your graphing calculator. We have a turning point here and a turning point here. So we've got 2 turning points for this one. And I'll go ahead and fill them in for the other 2. You have a turning point here and here. So the second one also has 2 turning points. And then the third one, you have a turning point up here, down here, and up here. So this third one has 3. Okay. Again, I'll fill out the rest of the information at the end here for these other 2 columns. We're going to focus mainly on the first column, but the turning points was easy enough. It's kind of good to show you where those turning points are. All right, let's talk about the relative minimum. If you put that into your calculator, you've got a relative minimum right here, okay? So you're going to do your left bound, your right bound, and then somewhere in between you'll take your guess, okay? So when you do your relative minimum, and we round it to 2 decimal places, you're going to get 1.33, 0.81. Okay, that's your x and y coordinates for that minimum. All right, relative maximum. That maximum looks like it's going to be somewhere along the y-axis. And when you put it in your calculator, you will indeed find that it is on the y-axis. It's at the point 0, 2. Okay, so for our increasing and decreasing intervals, you're going to use these x values, because remember, we use x values for when we talk about intervals. Okay, so first of all, let's do decreasing and increasing kind of as a pair. Okay, well, what are we doing first? We're increasing here, right? So we can go from negative infinity to, and it goes up to 0, right? Because that was our relative maximum. It was at x equals 0. So we're going to put 0 there. All right, that's our first increasing interval. Then we're decreasing from 0 to our minimum, which is 1.33. So 0 to 1.33. And then we start increasing again. So we pick up our increasing interval at 1.33, and it goes on to infinity. And there we've gotten our increasing and decreasing intervals from our approximations. You can kind of do the same thing with zeros with positive and negative intervals. You've got a 0 at x equals negative 0.84. So before that 0, we're negative. After that 0, we're positive. So our positive interval is going to be from negative 0.84 to infinity. Our negative interval is going to be negative infinity to negative 0.84. And so that's how you write some of that information in. Okay? I'm just going to go down the list of these other 2, and you can fill out this information as I write it in. And you can try this on your graphing calculator and see if you get the same results. So the relative minimum for the second one is at 0, negative 6. Our relative maximum is at 2.67 for our x value, and y value of 3.48. Our decreasing interval is from negative infinity to 0, union with 2.67 to infinity. Our increasing interval is from 0 to 2.67. Our 0, well, we've got 3 zeros in this particular graph. So we've got x equals negative 1.09, 1.57, and 3.51. So we have some positive intervals here, positive intervals starting at negative infinity and going to negative 1.09. And that's going to union with 1.57 to 3.51. Then we've got a couple of negative intervals, and those are from negative 1.09 to 1.57, union with 3.51 to infinity. All right, for this last example, we've got a relative minimum at 0, 2. We have a relative maximum. Well, actually, we have two relative maximums, because if you look at the shape of the graph, we have one here and we have one here. So our relative maximums are going to be at negative 1.41, 6, and at 1.41, 6. All right, our decreasing interval is going to be from negative 1.41 to 0 and union with 1.41 to infinity. Our increasing interval is going to be from negative infinity to negative 1.41 union with 0 to 1.41. And then we have two zeros. Our two zeros are located at x equals negative 2.11 and 2.11. And so we have a positive interval from negative 2.11 to 2.11. And then we have our negative interval from negative infinity to negative 2.11, union with 2.11 to infinity. Okay, so again, you can use this information to try it out in your calculator to see if you can come up with the same results. All right, that's going to end this video on section 3, where we talked about key features of higher order polynomials. In the next section, we're going to wrap up the unit by talking about graphing and writing polynomials.